So our next speaker of the day will be Matt Hogancamp, who will tell us about Khovanov-Rozansky homology and QT Catalan numbers.
Cool. Well, thank you for the invitation to be here. I'm very excited. Okay, so what I'm going to be talking about today, the main kind of subject is Khovanov-Rozansky homology, the triply graded Khovanov-Rozansky homology, which is a sort of rigorous construction of something, I guess, physicists like to call the super polynomial. So there are lots of conjectures about the Khovanov-Rozansky homology, but they're all very hard to prove because computations are insanely difficult in Khovanov-Rozansky homology. So I'll be talking about some progress in that direction. Okay, but let me remind you of kind of some background, which maybe you're familiar with, but it'll also give a kind of bigger picture of what's going on here. So decategorified, we have the Homology polynomial, which can be described in terms of a trace on the Heck algebra. You don't really need to know too much about Heck algebras, but let me say this anyway. So the Heck algebra, they're indexed by natural numbers, and it's defined to be, you take the braid group on n strands, the group algebra of the braid group on n strands, and you mod out by relation, which to topologists, okay, so any topologists in the audience may, well, I ran out of room. Let me write this here. So I prefer a somewhat strange looking scain relation, but whatever, that's fine. Okay, so this is a Q deformation of the symmetric group algebra, because if you set Q equal to 1 in that relation, you recover one of the relations in the symmetric group. So on this algebra, there is a trace. So this is a linear function from the Heck algebra to the ground ring, but you have an extra variable there. And the way it's defined is, given a braid, you close it up in the plane, and then you evaluate using the following kind of rules. So a right-handed crossing can be undone without penalty. A left-handed crossing can be undone with a slight penalty. And you can remove a circle at the expense of multiplying by this factor. Maybe I will utilize this board because I like to write very big, I guess. So I don't want to. You guys can all read this? Fine. Okay. And so the composition of these, so the Jones-Oakniano trace of a braid, you can look at a braid, its image inside the Heck algebra, take the trace of that. This is the Homology polynomial. Of the closure of that braid. So this link you get by closing up the braid is denoted by B hat. Okay, so that's the thing that's the categorification of this is what I want to talk about. But let me first describe a connection to combinatorics. So this talk is kind of a weird, it's kind of an interesting mixture between topology, representation theory, and combinatorics, and maybe some algebraic geometry under the rug. So it's a little bit, but let me talk about the combinatorics connection. Sorry, I'm getting ahead of myself. Before that, there's a sort of annular version of this story, which is, so given a braid, let me denote by brackets beta the closure of the braid inside the annulus. So you connect up the strands, but then you puncture the plane. So this can also be thought of as a conjugacy class of a braid. If you were to conjugate this braid, if you put a gamma up here and a gamma inverse down here, well, the gamma inverse slides around the circle and annihilates the gamma. So this is invariant under conjugacy classes. Oh, and that's a bijection. Okay. So let's let AN be the vector space. Spanned by all annular closures of braids, modulo that skein relation up there. So it's a theorem of Tarayev's that if you take all these guys, and you take the direct sum over all n's, this is isomorphic to a free commutative algebra. In other words, a polynomial ring. On the classes associated to these special braids, these 1 over n twists. So as n goes from 1 to infinity. So this is actually the source of the connection to symmetric functions. Is there a question? No? Okay. Okay, so symmetric functions. So let me set up some notation real quick. So f is going to be a field of characteristic 0. Usually it's rational numbers. This notation, lambda sub f, is the ring of symmetric functions in infinitely many variables. We only really are going to care about the case where f is either q or some rational functions. So this is just a little bit of notation. Okay, and it's very well known that this is also a free algebra on infinitely many variables, where En is the elementary symmetric function. Okay, so in this language, the Jones-Oconeanu trace can be described as a composition. So first you do, so you have this big direct sum. This is, in fact, isomorphic to the ring of Q symmetric functions via an isomorphism that takes our special braids to actually the most convenient choice. I don't want to lie. So actually the most convenient choice is not En, but a multiple of En. Whatever. And following up with a special map into this ring gives you the Jones-Oconeanu trace. Provided, so let me call this map evaluation, where that last map is the unique algebra map sending En to 1 plus A. Woo. Okay. So evaluation goes from generally any ring of symmetric functions to polynomials in A, and it's the unique algebra map sending En to 1 plus A, which, if you like a different description, given any symmetric function, what this is doing is it's picking out the coefficient of the Hoekscher functions inside that symmetric function. So you can describe that as the following polynomial. So you take the coefficient of this Hooke shear function. K is the size of the top row, minus 1. So that's a definition of an algebra map, and the assertion, which is pretty obvious from the definitions, is that the Jones-Oceaniano trace is this composition. Okay, so you can interpret the Humphrey polynomial in this kind of cool combinatorics language.
What's the index in the sum?
The width, the degree of the symmetric function. Sorry. If you take a degree n symmetric function, these are all hooks with n boxes. Okay. Okay. So now we want to categorify that because we want to categorify everything. So we want a T deformation. But I should warn you that we don't yet have a full rigorous picture of the T deformation. So you would like to just, maybe I'll say this sort of more formally in a moment, but unofficially, you sort of, to each braid, you would like to associate a QT symmetric function so that the evaluation, in a sense, of that QT symmetric function is some Poincare series of some homology theory. That's not quite right, but it's on the right track. So that's the sort of motivating philosophy here. Okay, so the categorification of the Humphrey polynomial is given by triply graded link homology. Although now there are actually two versions. There are two different. So the triply graded Khovanov-Rozansky homology is what I want to talk about. There's also recently a triply graded link homology constructed by Oblomkov and Rozansky, which I don't understand, so I won't talk about. So the triply graded Khovanov-Rozansky homology, the input is a braid. And the output is what people in the area lovingly call triple H of the braid, which is a triply graded vector space. Sorry. This is the category of triply graded vector spaces. And it satisfies, so the Poincare series is going to be a 3-variable function. Again, I ran out of room. So the Poincare series of this triply graded homology, defined in the usual way, satisfies, so the T here is homological degree. If you specialize that homological degree equal to -1, you recover a Humphrey polynomial up to a normalization, okay? So this is very hard to compute. This is a kind of theme. So I don't know, you can imagine everyone's surprised when there arose tons and tons of conjectures basically giving formulas for this invariance in terms of Hilbert schemes and so on. So the conjecture I want to talk about in this direction is due to Gorsky-Oblomkov-Rasmussen Shende from 2012, I believe, which gives a conjectured formula, really, for the for the Khovanov-Rozansky homology of torus knots, positive torus knots. So in this language, let me state their conjecture in the following way. So if you take the braid representing the NM torus knot, so TNM is my notation for the torus knot. These are positive and coprime. Then this is equal to the evaluation in a symmetric function sense of a particular symmetric function. That symmetric function is the character of a bigraded SN module. And that bigraded SN module is really a representation of a rational DAHA. Okay, so I can say it this way. Sorry, this is a little bit technical, but I want to, not write anything false. So you take the character of some module, depending on M and N. You take the character of that module and tensor with a sign character because of conventions. And then you do the evaluation of that, and you get the Poincare series of the torus knot modulo conventions. Okay, so here I'm using variables capital Q, A, T, whereas this guy. So the variables. This is a little bit technical, but it's actually kind of important, the change of variables here. So the little q on this side is actually big Q squared. The little t is actually big T squared Q to the -2. And the little a is related to big A in that way. Where, let me write this, LMN equals a filtered representation of the rational DAHA associated to SLN. I'm not going to explain what these words mean because we won't really need them. Eventually, the conjecture boils down to some combinatorial statement, which we'll use. But this is some filtered representation of the rational DAHA. Representations of the DAHA are naturally graded, always. So there's a grading coming from just the fact that it says representation. It's filtered. So you can take the associated graded. You sort of lose the action of the rational DAHA, but you keep an action of the symmetric group. And it'll be a bigraded symmetric group module. So the character lies in this QT symmetric functions. Okay, so this is basically a categorification of the previous kind of statement. So decategorified, we have a symmetric function to each braid, and then the evaluation of that symmetric function gives you the Humphrey polynomial. And this is kind of a categorification. So now, to the torus knots, we have a SN module, a bigraded thing. The character of that now computes the Poincare series of the Humphrey homology. So this is pretty cool. This is like what we wanted.
Is L a simple module?
L is yeah, exactly. L is a simple. In fact, it's the unique finite dimensional simple module of the rational DAHA for SLN.
And you said there's a grading and a filtration. Is the grading just the weight space grading for the SL2 inside
Yes.
the DAHA?
Yes. That's right. Okay. So I may be going a little bit slower than I want to, so let me okay. So what do I want to talk about next? Yeah, okay. So I want to talk about not all torus knots, because I can't prove this for all torus knots. That would be great. But I can prove this for some special class of torus knots. The case, so let me kind of recast, let me specialize this problem a little bit. So we are going to focus on the following torus knots. N, comma, nm plus 1. So in this case, we have the following kind of facts. So this guy, the trivialist of them, is actually the trivial SN module, one-dimensional, just totally boring. And its character is the trivial representation. If you twist by the sign character and then take character, you get En. Furthermore, you understand the operation of adding multiples of n. So in general, the character of this module is related to the character of, so if you add n to the numerator, it's well understood how the characters behave. So there's an operator on symmetric functions called, the combinatorics people like to call nabla. This is the Garcia-Bergeron operator. And sorry for teasing you, but I'm not going to define it. But this is, what you should think of is that this is the symmetric function analog. They didn't define it this way, but modulo all these conjectures, this is the symmetric function analog of the full twist operator. So given a braid, you can insert a positive full twist. This is like the Dane twist inside the annulus. That's a well-defined operator on actually annular closures of braids because the full twist is central. So this is the symmetric function analog of that operator. And that sort of philosophy is definitely consistent with what I wrote here. If you take the braid representing the Mn torus knot, perform a full twist, then you get this other torus knot. And this is saying, well, at least nabla respects that kind of philosophy in this particular case. So the character of the representation, anyway, so cool. Sorry, I didn't say that right. But performing a full twist on these braids, performing a full twist on this braid gives you that braid, and correspondingly, nabla gives you the correct, actually the predicted modules conjectures gives you the correct object. Okay. And so, I realize now that I made a mistake. There's an annoying 1 over q, 1 over 1 minus q here. You could work with reduced homology to get rid of that thing, but whatever. It's fine. And so we are now reduced to purely combinatorial statements based off the Gorsky-Oblomkov-Rasmussen-Shende conjectures, which was in this language, which was conjectured by them, but I can prove now. So this is the result I want to talk about. The Poincare series of the triply graded homology of these knots is actually the evaluation in the symmetric function sense of nabla m en. So again, I'm not going to really define nabla for you, and I'm not going to really focus on this side. Really, what I want to do is focus on this side, tell you how I compute this, and then I want to ask you to believe me that you kind of just compare the left-hand side with the right-hand side. So the right-hand side is the subject of uncountably many papers in combinatorics literature, and so there's just formulas for this thing now. So this is the subject of what's called the rational shuffle conjecture. There's like various versions of the shuffle conjecture, which are famous conjectures in combinatorics. And a conjecture is basically a formula for the right-hand side, but now it's a theorem by Anton Mellet. And well, so there are various versions of the shuffle conjecture. One of them was proven by Carlson Mellet, and then it was later generalized by Mellet in the past couple of years. So I think this was like 2015, and this was like 2016. Okay, so luckily for me, they tell me what the right-hand side is, and so I just compare my answer with theirs, and that's the theorem. Okay. So let's compute some stuff. So this is the kind of big picture. So, you know, I am ultimately interested in understanding more categorically the relationship between knot homology and these representations or Hilbert schemes and things like that. But for now, we'll have to settle for just evidence of those conjectures rather than the conjectures themselves. So this is evidence for those conjectures. Okay. Okay, so let me I didn't mention the big thing. So this conjecture, I erased the change of variables here. But the right-hand side involved variables q, little t, and little a. The main reason I even wrote down that change of variables was the following fact. The fact that the right-hand side has integer powers of t rather than half integer powers of t means that the Poincare series of the Khovanov-Rozansky homology up to that conjecture is supported in even homological degrees. So their conjecture has a consequence that the homology of the torus knots is supported in even degrees. And that means we should be able to compute it without actually doing any work. I mean, if you have a complex which you suspect is supported in even degrees, then you just filter it by subcomplexes where the subquotients are even. And then spectral sequence nonsense gives you your theorem. Okay? So in the end, I don't need to know very much about the original definition of triply graded homology. In the same way that you don't need to really know the definition of like singular homology in order to compute the homology of complex projective space. Okay, so I won't really give you the definitions, but it's okay, you don't need them. But I do want to pay my respects anyway to the origins. Okay, so so the categories I'm going to be working with are denoted this way. So this is the homotopy category of finite complexes of Soergel bimodules in type A. We have various structure on these categories. They are additive categories, so they have a direct sum. They are monoidal categories. They have a tensor product and an identity bimodule. They're graded, so there's a grading shift. And actually, they're triangulated, because I'm looking at complexes of the homotopy category of complexes. So there's also the homological shift. and distinguish triangles and all that jazz. So this is the categorical analog of a ring. In fact, this category categorifies the Hecke algebra. So this is the sort of correct, kind of understand this as the correct replacement for the Hecke algebra. So objects of this category, I like to denote them by certain kind of diagrams. Oh, sorry, I'm getting ahead of myself again. There's also an external tensor product that, you know, just like in permutations, you can take two permutations and place them next to each other, and you get a permutation of in a bigger symmetric group. There's a similar operation, the external tensor product. That takes you from two copies of Soergel bimodules and then gives you Soergel bimodules. Okay, so diagrammatically, I want to denote complexes and these operations in the following way. So a complex of Soergel bimodules is going to be denoted just by drawing a kind of a planar diagram labeled by that complex. And the number of strands is going to be equal to the index n. And the tensor product of two bimodules will be denoted just by vertical concatenation. The disjoint union, or external tensor product, will be denoted diagrammatically that way. Okay. So just like in the Hecke algebra, we have a map basically from the braid group to the Hecke algebra. And then a trace on the Hecke algebra will compute the Humphrey polynomial. So now let me mention a categorical kind of version of that fact. So Ruquier gave us invariant of braids inside the Soergel category. So given a braid, he defines a chain complex and tensor product of complexes respects the composition of braids. And I guess this definition was originally due to Khovanov. He defines a functor that plays the role of the Jones-Okeaniano trace. So given a complex of Soergel bimodules, he produces a triplet graded vector spaces. And then he proved that this guy is isomorphic to the Khovanov-Rozansky homology. So the Khovanov-Rozansky homology was not quite defined in this way, but they're more or less equal. I mean, unpacking definitions, they're actually equivalent. Okay, and so this is the context in which all that other stuff is occurring. So the triplet graded homology of a link is, well, you represent your link by a braid, you look at the Ruquier complex of that braid, and then you apply this functor. Just historically, why do we call it triplet H's? Well, because these things are complexes of Soergel bimodules, I have a functor called Hochschild homology. Okay, so Hochschild homology of a bimodule is always a graded object because you have, well, it's a derived functor of something. Since these are graded bimodules, Hochschild homology is a bigraded object. Since these are complexes of bimodules, the Hochschild homology of that is actually a triplet graded object. It's a complex of the Hochschild homologies of each piece. And then you take homology of that, and that gives you HHH. So the three H's are homology of the Hochschild homology of a complex. Okay. But that's too much. Oh, and diagrammatically, I'm going to picture this functor as just in that diagrammatics, I'm going to picture it just as the sort of Markov closure. Okay. So that's the background. Now how do I? Okay, so how do I compute stuff? So what do I erase? So now in this language, we want to compute this functor evaluated on the Rouquier complex of the following braids. You take these special braids, and you stack multiple copies of them on top of each other. So that's the braid that represents the n, nm plus 1 torus knot. And so we want to compute the homology of that thing. Okay. So as far as I know, there's no computer on Earth that can do this for like n bigger than 12 or something. I don't know, or 4. But okay. So how do we beat our computers? Am I missing anything? No, I'm not. Okay. I do want to say this though. So I've been sort of philosophically, what's kind of cool about this is that decategorified. Remember, so the Humphrey polynomial is an invariant of braids, but you can also extend it linearly to linear combinations of braids. And this is actually pretty cool because now you have not just braids, but you have more stuff there. And so a similar thing is happening here. We don't just have braids. We have actually any object of the Soergel category. So we have distinguished triangles. We have lots of techniques. So in particular, we have various long exact sequences. Okay, so the main kind of cool thing about passing to the Soergel category is that you now have more objects, and so you can use them in kind of auxiliary steps of a computation. So that brings me to the next thing I want to talk about, which is how do I compute stuff? So this is a technique introduced by me and Ben Elias. Okay, so how does it go? So first off, there's some special chain complexes of Soergel bimodules. These are like categorified Young symmetrizers, sort of. And so there are some chain complexes of Soergel bimodules satisfying the following properties. So first off, they are symmetrizers, which in this context basically means that they eat braids up to homotopy. And a shift, okay? I'll explain what this means in a second. And so that shift here is a homological shift and a Q shift simultaneously. These guys fit into a distinguished triangle. So this is really the source of the long exact sequences that I'm going to use to compute the homology theory, or to compute the homologies. So if you are not an expert in triangulated categories, that's totally fine. The following I'm going to state a corollary here in a second that will boil this down to the level of Poincare series. So you don't need to know really anything about triangular categories in the end. And then Q is this shift. Oh, yeah. Sorry. The boxes are labeled by K. So this is a Kn. Thank you. This is a Kn. This is a Kn plus 1. So these Ks are actually recursively defined. You can actually take this distinguished triangle basically as a definition of the Kn plus of the Ks. Oh, and maybe I should mention, just if you're curious, if you like representation theory and categorified representation theory and all that, these are like categorical analogs of the projectors in the Hecke algebra that project onto the sign representation, or maybe the trivial representation, depending on your preference. And this sort of complex represents the idempotent, which is the induced sign representation. So it's an item, kind of a quasi-idempotent complex. And as you know, if you induce the sign representation one level up, this splits into another sign representation and then something else. And so decategorified, there's actually a linear relation between this projector and that kind of thing. And this is a categorification of that linear relation.
Do you have one for the trivial representation as well?
Yeah, yes, I do, but it's not as pretty. Well, no, actually, it looks exactly the same, but yes, it works exactly the same way.
Does it have a long exact sequence?
Yeah, yes. But you can't use that guy quite as nicely in computations because there's this parity observation. So these guys are actually, as you'll see in a second, they're actually really useful for computations because they satisfy if you the technique that I haven't mentioned yet actually preserves evenness. So if you have a homology that I'll come back to that maybe in a second. But yeah, these are actually a little bit nicer than the main difference between these projectors and then the kind of dual the anti-symmetrizer, or the difference between the projections onto the sign and the projections onto the trivial. These guys are honestly unchanged by putting a braiding here. And decategorified, the same is true for the other projectors. But when you categorify, it's no longer true. You actually have an interesting braid group action on those complexes.
So if you're categorifying the trivial and sign representations of the Hecke algebra, one of those constructions is a lot easier than the other one. Is this the...
Yeah. No.
Which one do you think is easier?
Sign. But I mean, it maybe depends on your conventions.
Yeah.
I'd say sign.
One of the projectors is basically an object in commutative algebra. It's a projective resolution of something. The other projector is weird, and that's kind of what this is. Okay. Okay. Gosh. Okay, so as a corollary of that exact sequence, we have the following fact, which is suppose you have 3 chain complexes of Soergel bimodules. One of them looks like this guy, and then maybe some other stuff outside of that piece. We have a C minus, which is you do the same thing except with you switch all the crossings. And then you have C prime, which is you use a bigger, so the projector has grown by 1. Okay, so inside of these disks, our diagrams look as follows, and outside of the disks, they're just the same thing. Then, if this guy and this guy are even, which means that they're supported in even homological degrees, then if two of them are even, if these two are even, then so is the third. And then their Poincare series just add. So the Poincare series of C plus is the Poincare series of C prime. Oh, did I call it C prime? Whatever. C prime and plus Q times the Poincare series of C minus. Okay, so that's boiled down with the key sort of thing. Okay, and so now the technique which works sometimes is the following. So this is what we do. So start with a braid closure. And then perform a sequence of the following operations. So if you see a strand, you can put a little box in that strand. And now in these pictures, my boxes are all going to be KNs. So I'm going to leave off the actual decoration here. So you can add a box to a single strand up to a multiple. You can replace this object with this object. You can absorb braids. So on the top or on the bottom. These are actually true in the level of braids. There's no need to actually close up your diagrams. And then you also have the following relations. How much time do I have?
Till half past.
Till half past, okay. Cool. And by the way, these relations should be more or less clear from. Oh, let me just mention, actually 1 is a special case of 2. Okay? I didn't mention it, but K0, the box on 0 strands, is the identity. So a special case of 2 is 1. And then we have the following, basically, Markov-like moves. Which, because of the conventions I'm working in, have some weird shifts, whatever. So the right-handed curl can be undone with a slight penalty. The left-handed curl can be done again with a slight penalty. We won't actually ever use this. All our braids are going to be positive. And then if you take Kn plus 1, with 2 of its strands connected in that way, then you can replace it by this object. Okay, and then the theorem is that if this works, then it works. So if this actually results, oh, sorry, there's one more. The circle, the undecorated circle, is 1 plus a over 1 minus q. I guess maybe that one follows from those two. I guess this follows from 1 and then this relation. But whatever. So if this actually produces an element, So we might have half integer powers of t or q, but as long as it's just an overall factor, then this is actually the Poincare series. Okay, so that's the technique. And the reason is parity. If you have only integer powers of t, then this means that the corresponding Poincare series is even. And so the spectral sequence argument that's underlying the application of these exact sequences is trivial. Okay. So using this, I guarantee every one of you can now compute lots of invariants of lots of things, even if you've never even seen the definition of Khovanov-Rozansky homology. This is how you compute it for lots of stuff. It almost works for the figure 8, but it it actually does. But you have to be clever, or you have to compute the same thing twice, and then it's a spectral sequence argument. But you can do lots of computations without even knowing the definitions, which is great, right? Okay.
From the store, do you also get some kind of distinguished cycles that have some sort of representation theoretic significance, or at least in the collection of torus knots that you were looking at?
That's a really great question. Yeah. So the reason actually why we came up with this way of computing things is because me and Ben, we wanted to compute actually special classes in the homology of the n torus knot. The reason is that there's a categorical interpretation of these homology groups as actually homomorphisms, some kind of derived version of homomorphisms from the identity into your braid. And we want to compute some distinguished classes in here, so we computed the whole thing and then just pick out the classes we wanted. Yeah, exactly, yeah. But I don't know how to interpret a general class, but there are some special ones, yeah. And we can talk later about why they're special. They're eigenmaps, but okay. Getting ahead of myself. Okay, so just some examples. The unknot is you can put a box at the expense of that factor, and then you can evaluate that. So you recover the previous value of the unknot. If you want to compute the trefoil, here's what you do. You start with a full twist, and you put up to a factor of 1 minus q. This annoying factor of 1 minus q is actually canceled by putting a box there. And then you apply this relation, and you get. Okay, and since actually those relations hold on the level of braids, you can then take this and put another crossing on top. And now, since this guy absorbs crossings, you have that, and then you can close up everything and compute. And I won't do it because this is really easy, but you get the invariant of the trefoil like that. So it's really quick. Okay, so now I can at least state what is the main. Let me leave that up there. No, that's not what it. Okay. So now I'm going to state the computation. I'm going to actually focus on the case m equals 1, so the n comma n plus 1 torus knot. But it generalizes to general m fairly easily. Okay. Definition. So I want to define a family of complexes that basically interpolate They're basically the auxiliary, like the intermediate steps in a computation like this. So I want to compute the homology of some knots recursively, and the intermediate steps are some sort of auxiliary guys which turn out to be important in their own right. So the auxiliary guys are right here. So for each binary sequence, define a complex of Soergel bimodules so these actually fit into a sequence. So there's a family of them for each m, but I want to focus on just a case where an m is 1. And I'm going to define them by example. So the complexes look like, so you take the full twist braid and then the symmetrizer braid, and your sequence of zeros and ones up top, and then you connect. So each 0 goes to the k box, and then each 1 goes to the full twist box. And then you do the reverse on the bottom. Okay, so those are some kind of cool looking chain complexes. And let me also introduce notation. X is going to denote this special braid. Then the theorem, the main computation, is actually a formula. And if you pay attention to nothing else in the talk, you can at least appreciate the formula. I think it's kind of, I don't know, it's kind of amusing that you actually get a formula at the end. So the theorem, the computation is that the Poincare series of those chain complexes with the extra crossing, or the extra kind of 1/n twist on top, where these polynomials are defined by the following recursion. So the empty sequence is 1. So this gets the recursion started. This tells you what to do if you have a 1 at the beginning of your sequence. If you have a 0 at the beginning of your sequence, there's actually 2 cases. If you have 2 zeros, then there's some power of t. It's the number of indices such that vi is 0 plus 1 because you have another 0 plus a. So you can see that this is basically going to come from an application of that rule up there. You're kind of decreasing the overall width of your braid while multiplying by some factor. And finally, sorry. Okay, so this uniquely defines a family of polynomials, and what I'm saying is that those are the Poincare polynomials of these complexes. So in particular, if V is the all ones sequence, then you get the n plus 1 naught. So in particular, G of the all-1 sequence is the Poincare series of this complex. But on the other hand, that complex is just a full twist. You have no K, it's just a full twist, but with a okay, so this is the Poincare series of the n plus 1 naught. There's a more general recursion that works for all m's, but I won't state that. And so as a corollary, just by comparing formulas, you get the thing that I ran out of time, but you can see something so simple can be interpreted computatorially. If you're curious about where the Catalan numbers actually come out of this recursion, you can ask me over lunch. But I think I ran out of time. So, thank you. I didn't mention this, so I'm sorry, but I should because I'm being recorded. So the case m equals 1 was actually first conjectured by Gorsky, and so this actually predated all of these like really fancy conjectures about DAHAs and Hilbert schemes. Gorsky just kind of noticed it, and in 2010. So I wanted to acknowledge that. Sorry.
Question? Before evaluating, is this sort of recursion something that shows up in symmetric functions?
Yeah, actually. So you can. I don't think these particular symmetric functions are, and they have not exactly appeared in combinatorics literature. But if you extend those definitions to these if you extend those definitions in a somewhat natural way, you do actually get symmetric functions that satisfy this recursion. So let me just say, under this correspondence between symmetric functions and complexes of Soergel bimodules that should exist, but no one knows how to construct yet. These guys, these special complexes, are analogs of Hull-Littlewood polynomials. And yeah, if you take those definitions, yeah, they satisfy this recursion. There's another question.
So all that was about like Humphrey or this homologies in ordinary, fundamental representation, so to say.
Yes.
And there are some ideas to consider more general colored
Yes.
representations. Do you have any?
Yeah. So I can do this for. So this also works. I guess I haven't really written this down, but this should work for symmetric powers as well. For anti-symmetric, for wedge powers of the fundamental, probably also works, but I'm less sure about that.
So is it typed somewhere, maybe, or
Say it again?
is it like written down somewhere, or
Like the formulas for those things?
For symmetric ones.
Not yet. I'll let you know when it is. Yeah.
Maybe this is related to the last question, but I mean, how does the technique work on like cables of torus lines?
Oh, yeah. So it's a good question, and I haven't looked at that. I've been absorbed in like what I just showed you for a little while. So yeah, so it'd be natural to try to do more general algebraic knots, like cables of torus knots by other torus knots, or cables of torus knots by other things. And it should, I haven't thought about it, but this should work. Like anytime you're in a situation where, somebody's conjecturing a formula for your knot invariant, and it's positive and has like only even powers of t, something like this has a hope of working. So I invite everyone to try it. I don't know, it's fun. Yeah.
What about other torus knots? So they are still positive? I mean, I know
They are still positive, yeah, it's-
generalization. So.
Yeah. That's a good question. So there are other torus knots. This actually works for things, by the way, that are not torus knots, which is interesting because this is a situation where we may not actually have formulas for them, but now we do.
What about twist knots?
Say it again?
Twist knots?
Twist knots. Again, really great examples. Yeah, I haven't thought about that. That would be another like good place to look, or like pretzel knots too, maybe, but maybe not. But about your torus knot question, sorry. You can more generally look at this family of complexes where you start with the C's, and then you stack. There's a more general family called that are indexed by M's, which I didn't write down, but I can tell you what they are. You could also, stack powers of X on top. And a relation of this type actually will hold in general. So you always kind of get this cool. You always get a sort of recursion that looks like this, indexed by not necessarily binary sequences, but by sequences inside here. So if you're looking at grades of width n, and you have like basically m full twists that you're putting on your thing, your complexes will be indexed by these sequences. And there are recursions that reduce you to the case when your first number is a 0. But how you deal with the 0 at the beginning is a lot harder when r is bigger than 1. So I don't have an answer there, but it would be.
Is it a matter of brute force or you need, I mean, with your axioms, can you do that? In principle, I'm not.
I believe so, but I don't know how the recursion looks yet. Yeah.
I just had a question about it. So, did I understand you correctly that these polynomials here are related to Hall-Littlewood polynomials? Is that what you said?
Yeah.
Okay. So I just wanted to mention that the character formulas that we wrote up are actually just Hall-Littlewood.
I heard that in your talk, and I was like, my ears perked up, and I wanted to ask you about that as well. But how they sort of appear in this context is, so there's a paper, Haglund, Zebrowski, so the compositional shuffle conjecture, Jim Haglund and Zebrowski and, is it Remmel? I don't know. I know I'm not crediting all the right people, but what they do is they prove that the elementary symmetric function is a sum of Hall-Littlewoods. And if you want to understand nabla of En, you should try to understand nabla of these. So this is like a refinement of the original shuffle conjecture. And these pieces are basically, you can see, so these are indexed by compositions of n, but compositions of n are in bijection with binary sequences in which the first element is a 0. So in fact, their refinement is kind of basically mirrored in the recursions that come out of this story. So. But there are different versions of Hall-Littlewood's too. So these could or could not be the same ones as you have.
All right, well, let's thank Matt again.